Lorentz violation unveils mysteries of dark energy stars and prevents singularity of black holes. The universe's structure is more mysterious than imagined. Scientists are intrigued by dark energy and peculiar star behavior. A new study suggests minimum speed might unlock these secrets, challenging our understanding of spacetime and potentially reshaping our universe view. A study in physics of the dark universe introduces Lorentz violation with an invariant minimum speed as the foundation of gravitational Bose-Einstein condensate for dark energy stars, revealing complexities in quantum vacuum and spacetime, led by Dr. Cláudio Nassif Cruz. Dr. Cruz suggests an invariant minimum speed, tied to symmetrical special relativity, alters spacetime structure. This speed, linked to the Planck length, affects GBEC formation in dark energy stars, potentially solving event horizon singularity issues in gravitational collapse scenarios. Our study shows that the presence of an invariant minimum speed in the fabric of spacetime leads to a phase transition between gravity and anti-gravity, which prevents the formation of a singularity at the event horizon. The study reveals a repulsive core, described by a GBEC metric, replaces the black hole's event horizon. This core, enveloped by a phase coexistence region, bridges gravity and anti-gravity, linking the cosmological constant to the invariant minimum speed. Dr. Cruz's study introduces an SSR metric with a minimum speed, enhancing the understanding of vacuum energy beyond the de Sitter model. It challenges black hole theories by eliminating singularities and introducing a phase transition region. This revolutionary approach bridges quantum mechanics and general relativity, highlighting the fundamental role of minimum speed in physics and cosmology.